Hello, welcome to this video. I am your host, Mr. McMahon. These are some of the notes we went through last class. So we didn't get to all the problems. I want to go ahead and just finish the rest that I had queued up. I was able to do this with the Block 1A class, but I've also got some bonus questions at the end just to kind of round out some of the stuff having to do with rotational inertia and angular acceleration, sort of how they're related to each other, even in different cases, different kinds of mass distributions. So we ended up solving this falling pole problem at the very end of class. I just want to pick up right here. And we've got two more problems after that, and then there's my sort of bonus problem, right? So let's just go ahead and get started. Hope you guys are having a good async day. Those darn seniors are keeping us from meeting together, unfortunately, but I'm sure you're enjoying being home. I definitely am. But anyway, we got a propeller of a airplane engine. We are given a torque. All right. So this is a torque already. So we don't have to worry about where's the force being applied, how far away from the center. It's already baked in here. It's already calculated. It drives a 2 meter long, 40 kilogram single blade propeller. On startup, what does that mean? It means our initial angular velocity is 0, right? The propeller is not moving initially. The engine starts to rotate. How long does it take to reach 2,000 RPM? And remember, RPM stands for rotations per minute. So we might have to do some unit conversions later. Also notice, right, this is sort of a continuous we want to treat this almost like a uniformly distributed rod of some sort. So this is a case where I'd have to give you the moment of inertia formula for this specific object. So the moment of inertia or rotational inertia for this propeller, if you remember some of the formulas, this one would be the one that is mL squared over 12. L being the entire length, which they just straight up gave us, right? Now, if the axis was going through maybe one of the ends down here, we would actually have a 3 at the bottom instead of a 12. But in this case, we have a 12, right? It's for a specific situation where you have some kind of uniformly distributed rod and you're rotating about the very center of the rod, right? So that's this specific rotational inertia formula. So we want to find how long does it take to reach 2,000 RPM? And this is a non-equilibrium situation, right? Things are accelerating. So a good place to start, whenever you know that the sum of the torques is not equal to 0, it's just to go ahead and set up Newton's second law, right? But for rotational motion, right? So instead of force, we have torque. Instead of mass, we have rotational inertia. And instead of acceleration, we have alpha, right? Same basic equation, but now just made rotational. So sum of the torques. Well, we know we have only one torque acting on the propeller. It's the 500 Newton meters. And even if you were to count gravity working on this propeller, gravity is going to act at the very center, going straight down. And so the torque, right? Torque is force times R. The R, due to gravity, or the R, the distance from the axis, is 0. So the torque due to gravity is also 0. So this is the only torque we have. And we want the rotational inertia, which is going to be the mass of the propeller times the length squared over 12. So we have 40 times the length squared. That's going to be 2 squared over 12. And we do not know what alpha is, but we do know that we have a very nice kinematic that involves alpha and that involves omega, right? So if we're thinking how long, we know we want time. we have alpha, and we have omega, right? This would be omega final, the 2000 RPM. So if you think about it, we know we're going to have to use this kinematic at some point, right? The only thing we need to do is we just need to solve for that alpha, right? We already know this is 0, and we know this is the 2000 RPM, right? So if we can just find alpha, we can solve for the time there. And we have a nice little equation to do that over here, right? Newton's second law. Cool. So this is going to be 500 newtons times meters is equal to 40 times 4. That should be 160 over 12 times alpha, right? So alpha is going to be, I'm not sure why I'm writing the units here. It's just sort of force of habit, but I'm not writing it on the right side. Not sure why I'm doing that, but that's okay. All right, so times 12 divided by 160, I get that alpha is equal to 37.5. The units here would be radians per second squared, right? Is that what we would have? Let's see, the 40 was kilograms. The 2 was in meters, and the 12 was unitless. So yes, we would have radians per second squared. You just got to keep in mind, right, you can have different kinds of units, right? We could have ended up with rotations per second squared. So just be very careful when you're solving these problems. What units are you using? So 37.5 goes in for alpha. And now we're in a bit of a pickle because we have RPMs here and we have radians per second squared there. We've got to make sure we're using one or the other. We could actually turn everything into RPMs, or we could use radians per second squared for everything. Doesn't really matter either way. I like SI units. They're a lot more convenient when you're doing some other things. So I'm going to go ahead and convert the 2,000 rotations per minute. I'm going to convert that to radians per second, right? We know that there are 2 pi radians in 1 rotation, and we know there is, in 1 minute, there is 60 seconds, right? So the minutes cancel, rots cancel, and we will be left with radians per second. So 2,000 times 2 times pi divided by 60. Let's see why I'm in scientific mode for some reason. Okay. 209.44. 209.44. This is going to be radians per second. This is our omega final. 209.44 radians per second. Our alpha is 37.5 T. That means T is equal to 209.44 divided by 37.5. Right, notice how the units should all work out to just seconds, right? So divided by 37.5. So I am getting an answer of 5.559 seconds, which I believe is roughly what we got for block 1. One thing to notice is you could work in rotations per minute as well, right? So you could convert this to rotations per minute, right? You could, you could do this little thing, second squared, right? Or can we? Actually, you know what? I don't want to say that necessarily because of the second square. Does that throw a wrench in things? Not totally sure. Maybe I shouldn't risk it, right? So maybe just going forward, make sure you're in SI units, right? 5.59 seconds. Cool. All right. Now here's where we have a trickier problem. And actually for this problem, I made a slight mistake when I went through this with block 1A. I'll show you what that mistake was. It's already in the notes. If you looked at the notes, you can see it. But anyway, let's go ahead and just read the problem here. So we have Josh has just raised a 2.5 kilogram bucket of water using a winch. He accidentally lets go of the handle, right? So now the bucket is just falling and pulling on this sort of wrapped cylinder, right? So it's pulling with some kind of, gravity's pulling on the bucket pulls on the rope with some kind of tension force. The tension force then pulls on the, the cylinder, right? So we have tension forces, we have a force of gravity going down here. And for the bucket to be falling, we know that the force of gravity is bigger than this force of tension, right? Magnitude-wise. So that might be important later. So anyway, we got the rope wrapped around this cylinder. It's a 4 centimeter diameter cylinder, which means that the radius is 2 centimeters. They already gave that to us. Actually, I think this whole diagram wasn't supposed to be given, but I just included it anyway. And it rotates on an axle through the center, right? So we have this sort of solid cylinder, and chances are, whenever you're dealing with rotational motion and certain solid objects, you're going to need to know the rotational inertia formula for said object, right? So the rotational inertia of this cylinder, if you have a solid disc or some kind of disc-like thing, which this cylinder is, we would use this formula here. Right, so this works with discs that are solid and also with cylinders, because if you think about it, right, this is just a bunch of discs that are sort of added to each other. Right? Just a bunch of discs that are stacked on top of each other that all have the same rotational inertia formula. So we can use the same formula here. In fact, you know what? We might as well go ahead and calculate that. I know we're going to have to need it. We're going to need this number. So 1/2, the mass is 3 kilograms. And the R is 2 centimeters. Let's go ahead and convert that to SI units here, so meters. That's 0.02 meters. And that's squared. So let's just go ahead and get that number here. 3 divided by 2 times 0.02 squared. Am I in scientific? 6e to the negative 4, so that would be 0.0006. And the units here would be kilograms times meters squared. Might be nice to write that down. Okay, so we're going to need that. But the point is, what this problem is doing is it's trying to draw a relationship between linear motion, right, the linear motion of the bucket, and the rotational motion of this cylinder. Right, so one thing we also might want to keep in mind is that there is a connection between how this bucket accelerates linearly and how this cylinder rotates accelerationally. And if you think about it, the connection is that connection I've been trying to draw y'all's attention to for the past week and a half or so. And that's if you take a rotational unit, something like rotational acceleration, and you multiply by the radius of said, rotational acceleration quantity, you will get the linear counterpart of that quantity. So think about, right, this thing. This is the rope, and the rope goes down like this. The rope is going down, and it has some sort of linear acceleration. Think about the rotational acceleration, the alpha, of a point at the very edge of this cylinder. And that point is actually an exact distance, capital R, away from the center, right? We learned not too long ago that omega times R equals V, right? Theta times R equals, displacement or change in X. And we also learned that alpha times R gives you A, right? So this is a case where that applies. One thing you have to be careful about, though, is that our acceleration here has positive and negative sign to it. So it's going down, which we usually say is negative acceleration, but which way is this cylinder rotating? Well, if you look at the picture, it looks like it's rotating counterclockwise, which we call positive rotational acceleration. And the difference in signs here actually leads to a huge mistake. It will give you the wrong answer here. So what we want to consider is actually just the magnitudes, right? The magnitudes of these two things are related by times r, right? So that will be important later. Okay. Notice one thing that they didn't give you was the size of these tension forces. We don't know the size of those tension forces. The only thing we really can figure out is the force of gravity, which if this is 2.5 kilograms, that's going to be about 25 newtons, but we don't know tension. But it turns out that's actually not going to matter too much, right? So at this point, what you want to do is you want to just trust Newton's second law, just apply it to whatever you see, and then figure out, how can I use this mathematically? So maybe I might start with the bucket, right? So the sum of the forces on the bucket is going to be equal to the mass of the bucket times the acceleration of the bucket. And again, keep in mind, I'm going to think about just magnitudes here, right? So I'm not going to worry about positive and negative. So I'm going to put these absolute value bars. What's the magnitude of the sum of the forces here? Well, we know the force of gravity is bigger than tension, right? So I might write it as 25 minus t. We know that's going to be some positive number. M is 2.5. And then we have A, right? Just the magnitude of the acceleration, the size of it. Okay, so that's one equation. What's maybe another one? Well, we could also analyze, because this cylinder is rotating, we could analyze Newton's second law, but in a rotational framework. So we could say, what about the sum of the torques on the cylinder, right? So this is for the bucket. The bucket is not spinning or anything, so we're doing linear stuff. And then over here we have the cylinder, which is actually rotating. So we want to use all the rotational versions of stuff. So this is going to be I of the cylinder. And then times, let's think about the magnitude of this acceleration, the rotational acceleration of the cylinder. Okay, cool. We actually already have I. What is the torque on the cylinder? Well, if we look at it, right, we have a tension force, and it's a distance of capital R from the center of rotation. It's at a 90-degree angle too, so we have sine of 90 essentially, which is 1. So what this means is the only torque acting on this cylinder is that tension force, tension, times the radius from the axis of rotation. Right? That's it, right? There's no torque due to gravity because the R for that torque would be 0. So it's 0. So this is the only effective torque. And we already know this. Oh, in fact, we already know R, right? They told us R was 0.02 meters. So let's put that in. And then we have rotational acceleration of the cylinder. Again, we're just trusting Newton's second law, and it should lead us to the answer here. And it actually does. We just might have to be a little creative. So we notice we have 2 equations, but there's 3 unknown variables. However, we can reduce that down to 2 by bringing in this relationship over here, right? So this is super, super helpful because I can replace this acceleration here with alpha times r, right? And so I get a very, very useful second equation. We get 25 minus t equals, well, r is 0.02, right? So this would be 2.5 times 0.02 times alpha. And now check this out. We have 2 equations. There's t, there's alpha. We have 2 equations, 2 unknowns. That is a solvable system of equations, my friends. So here's how I might do it. First off, let's figure out 2.5 times 0.02. Okay, so let me go ahead and simplify this thing right here. This is 0.05. times alpha. And then let me go ahead and let's go ahead and solve this for t. So actually, let me do this a little differently. Let me add t to the other side and then subtract away the 0.05 alpha to the other side, right? So you should get this. There we go. And then what I'm going to do is I'm going to substitute it in to that first equation, right? So we get 25 minus 0.05 times alpha. That's substituting in for t. We have 0.02 is equal to 0.0006 alpha of the cylinder. Oh, I guess we don't need to write that anymore. Just alpha. Let's just call it alpha. Okay. 0.0006 divided by 0.02 is equal to 0.03. So we have 25 minus 0.05 alpha equals 0.03 alpha. And let me go ahead and add those like terms to the other side. All right, so I'll get 0.08 alpha. And if I solve for alpha, 25 divided by 0.08 is 312.5. This will be in radians per second squared, right? Cool. Yeah, we didn't have any rotations involved. We just all had nothing but radians and SI units, so we should end up with radians per second squared. Cool. And what's really nice is we can now very easily convert this to the linear acceleration of the bucket, which is what we actually need, right? Because we're trying to find how long it takes for the bucket to reach the water, and we know how high it is. So we need that linear acceleration. Just take that alpha and multiply by r, right? So 312.5 times 0.02. And that gives you a linear acceleration of 6.25 meters per second squared. And in block 1, we actually got an acceleration of 25 meters per second squared, which is physically impossible, right? It's physically impossible for an object in free fall, especially if it has a force pulling up against gravity, to have a higher acceleration than just an object falling in midair, right? So that was impossible, and that's why I looked back at this solution, figured out our mistake was we didn't consider magnitudes, right? We were actually working in some signs that threw off our final calculation. So you should expect a number less than 9.8, right, meters per second squared, because there's a force sort of working against gravity here, right? Okay, so we want to find how long it takes to reach the water, right? So we have our buckets, and we know the distance to the water here is, what does it say? 4 meters. We have the linear acceleration of the bucket now, right? That's its acceleration going down. We have change in x. We also know that the bucket starts at rest, 0 meters per second, right? That's what kind of assumed. Released from rest. Didn't underline that very well. And there's a nice little kinematic that also works in time, right? Change in x should equal v naught times t plus 1/2 at squared. The change in x would be -4. V naught is 0, and we have 1/2, right? This would be a negative acceleration, so negative 6.25 meters per second squared times, oh wait, this is what we're trying to find, t squared. And so now we just solve for t. So we end up with -8 divided by -6.25. Take the square root of that big thing, and this should give us our final answer here. 8 divided by 6.25. Bingo, bango, bongo. This is 1.13 seconds. Awesome. So that was a really intense problem. This is not something that I would give you guys on a quiz. Wouldn't be quite this hard. The problems I would give would be more typical of this propeller problem, the pull, and also probably this gyroscope. But, this is maybe a little bit too involved and a little bit too math heavy. I wouldn't want to get bogged down in a system of equations on, rotational motion. Rotational motion is hard enough as it is. So anyway, let's go ahead and do the spinning gyroscope. A gyroscope is a top-like toy consisting of a heavy ring, right? So what that's kind of trying to signal to you is that you're going to use the rotational inertia formula for hoops or rings. So that formula is super easy. It's actually just mr squared. Again, you don't need to memorize that. I'm going to provide it to you. Okay. The axle and the ring are free to turn on bearings to get the gyroscope spinning. A 30-centimeter long string is wrapped around the 2-millimeter diameter axle, then pulled with a constant force of 5 newtons. Right. So in this diagram over here, what's really nice is they actually converted everything for us. So notice how it's all in meters, right? Newtons, kilograms, radians per second. But keep in mind that's something you're going to have to do, right? Essentially you would see something just like this without the diagram. You need to be able to convert that stuff, right? So if the ring's diameter is 5 centimeters and its mass is 30 grams, at what rate is it spinning in rotations per minute once the string is completely unwound, right? Interesting. Okay. So where do we begin? Well, if you don't know where to begin, a good place is maybe start calculating the rotational inertia of something that you know you're going to use, right? We know we're going to analyze this spinning gyroscope thing. So the rotational inertia of the gyro is going to be the mass of the gyro, which is 0.3 kilograms times the radius squared. That would be the radius of the outer heavy ring, by the way, right? So this capital R that they have, that would be 0.025 meters. 0.025 meters squared. Okay, let's go ahead and calculate that. So that will be roughly 0.0001875. Cool. That'd be kilograms times meters squared. Okay, we know we're going to need that. Another good place to start, as always, is Newton's second law. I tell you guys this over and over. Always start with Newton's second law. Again, this is in the rotational sort of framework, right? So it looks like this, but it's Newton's second law, no matter, regardless. So what are the torques acting on this gyroscope? Well, we have a tension force that's sort of pulling here. Notice how it's pulling a distance. This is what they call little r from the center. This is that 0.001 meter distance. And with a tension force that we now know, that's 5 newtons, right? So that should be the only torque happening in this sort of plane of motion. Of course, there's gravity, right? But gravity is going through, it's going into the page, and it's along the axis of rotation regardless. So the quantity there is 0. The torque is 0 due to gravity anyway. There's only one torque that's actually affecting the system. So it's going to be the 5 newtons times the 0.0001 meters, right? The angle between those is 90. Oh, okay, it's 0.001. My bad. 0.001. Okay, we have the rotational inertia. That's 0.0001875 times alpha, right? So let's go ahead and find that rotational acceleration, because we can. You know what? Let me go ahead and just put all this into my calculator. 5 times 0.001 divided by my last answer, 26.67. Right. By the way, that's a nice trick if you don't know. Press the second button and the negative sign at the very bottom. It will just put your previous answer into the calculation automatically. It's really nice. So this would be radians per second squared. Right. Also, if you do it that way as well, your calculator will use all the decimal points associated with that number. It's not going to be some rounded number, right? So it'll be more accurate. There's my alpha. Okay, and from this point, you can actually kind of do this in multiple ways. Because if we completely unwind this string, you can kind of think of this as sort of like a change in x, right? Some sort of distance. And we know if this string is not slipping, that there's a relationship. We know that delta theta times r is going to equal that change in distance. So what we could do is we could start with that distance, calculate what the change in theta would be, and then use this alpha as it is. Or we could do something different. We could do alpha times r would give you the linear acceleration. Well, actually, maybe that actually wouldn't be super helpful. Let me maybe stick with that first idea, right? Because the goal here is they want the rate at which it's spinning. We want to be in this rotational framework at the end. So let's go ahead and just make everything in it, find all the rotational things, right? We want to find the final omega final, right? So this actually might be more helpful of an approach. So the delta x, that would be our L quantity, 0.3. The question is, do we use capital R or lowercase r? I know I wrote capital R. I was being a little careless, but which one do we actually use? Well, we use the one at which point the rope is actually acting on the system. It's acting at this distance, lowercase r. So I would actually want to use that lowercase r right there. So that would be the 0.001, right, and then times delta theta. So if my string unwinds a distance of 0.3 meters, then that corresponds to an angular distance of 300 radians. That's what we just found out. Yeah, and make sure you have the same units when you do this, right? These have to be the same, otherwise you are not left with radians. You are not left with radians. So that's our delta theta. How do we tie all this together to find this is omega final. This is our goal, right? We don't have any information about time. So if you think about it, there's only one kinematic that's going to do the job. Omega final squared equals omega initial squared plus 2 times alpha delta theta. Omega final is what we want to find, right? So omega final squared. Omega initial is 0, right? The gyroscope is at rest initially. And then we have 2 times alpha times delta theta. That would be 300. And of course, we want to take the square root of that. So the square root of, let me use the magic of notability here. Nice. So this should give us our answer here. Cool. Square root of 2 times 26.666, repeating. Okay, and then times 300. Oh, whoops. 300. Okay, and I took the square root of all of that, and I'm getting an answer of 126.49. What are the units? These would be in radians per second, right? So we have actually one more step because we want the answer in RPMs, right? So just do a quick little unit conversion, right? This would be radians per 1 second. There are 2 pi radians in 1 rotation, and there are 60 seconds in 1 minute. Right, you got to make sure your units all cancel. Seconds with seconds. All right, so take your previous answer times 60 divided by 2. Well, let me put 2 pi. And we get a final answer of 1,207.90 RPMs. Nice. And if you've ever had a toy gyroscope, this actually seems like kind of a reasonable answer. You can spin them pretty darn fast. I got one from Cracker Barrel when I was really young. Really cool little toys. Really cool stuff. All right. Hopefully you haven't tapped out yet. Got one more problem for you. So I've actually hand-drawn these 5 different objects. I made sure, though, to make them all the same weight, right? So each of these objects is exactly 40 kilograms, and they have some similarities, right? They're 4 meters wide from different, angles and whatnot, but their mass distributions are totally different. And the question is, if I apply the same torque of 5 Newton meters to each of these objects, let's try to see how their rotational accelerations are comparatively to each other. And before we do any calculations, you could probably make a guess. In fact, you could probably, if you know what rotational inertia actually is, you could probably get the right answer without calculating anything. But I'm going to go ahead and do the calculations anyway, just so we can see what the answer would be, like numerically. So make your guess, right? Try to guess which one would have the greatest acceleration, right? Which one would be the easiest to spin? Which one would be the hardest? That would be the one that has the least rotational acceleration to it, right? So make your guess. All right, let's go ahead and calculate. So first things first, let's find the rotational acceleration of this object. So it would be the sum of each mass times its respective radius squared. That's what that means. So this is going to be 10 times 2 squared plus 10 times 2 squared plus 10 times 2 squared plus 10 times 2 squared. There are 4 of these, so I'm going to go ahead and just say 4 times 10 2 squared. So this is going to be 4 times 10 times 4. That's 16 times 10. That's 160 kilogram meters squared. And from your formula sheet, we know that alpha is equal to the sum of the torques over I, right? So this is a nice variation of Newton's second law, right? It's just solving for alpha. And our torque is 5 newtons times meters. We have over 160 kilograms times meters squared. One really nice unit thing, right? If you convert the newtons back to what they're supposed to be, this is kilograms times meters per second squared. Notice how the units cancel perfectly, right? And they should end up giving you radians per second squared. So meters and meters on top cancels with 2 meters on the bottom. Kilograms and kilograms cancel. Notice how we're left with 1 over seconds squared. All right, let me get the number here. 5 over 160. So this would be 0.03125. We might say this is inverse second squared, or you could also say radians per second squared, because remember, radians don't actually exist. They're a ghost unit, right? So some depending on what videos you're watching, what professors you're learning from, they might use them interchangeably. Okay, cool. Now we have a rod which is rotating about this axis at the very end, right? So there's actually a formula for rotational inertia here. So for a rod of length L, the rotational inertia formula for this scenario would be mL squared over 3. And so we can just directly calculate that. This is also good practice with just using these rotational inertia formulas too, which is why I wanted to do this problem. Okay, let's get an answer here. 40 times 16 over 3. It's going to be 213.33 kilograms meters squared. So notice this has a bigger rotational inertia. So what does that mean for the acceleration? Well, rotational acceleration is sum of the torques over I. So this is going to be 5 over 213.33. I'll skip all the unit nonsense, right? So we can just get right down to the answer. This is going to give us a smaller rotational acceleration, 0.023 radians per second squared. Interesting. So it is harder to spin this rod as opposed to the figure above. What about this rod? This rod is spinning around an axis at its center. The rotational inertia formula in this case is mL squared over, in this case it's 12, right? So in fact, you could also just use the previous number. It's off by a factor of 1/4, right? So we would divide that number by 4. But I mean, you can see this as well if you just plug in the numbers, right? 40 times 4 squared over 12, right? What is that going to give you? 40 times 16 over 12, we get 53.33 repeating. All right, let's look at the alpha. That's going to be sum of the torques over I. That's going to be 5 over 53.33 repeating. 5 divided by that answer is 0.094 radians per second squared. Cool stuff. All right, so our rotational acceleration was bigger in this second rod as opposed to the first because it's easier to spin. Its mass distribution is not quite as large. And it's bigger than that first situation up here too. So let's see. Here we got a solid disk. Rotational inertia for a solid disk is 1/2 mr squared. So it's going to be 1/2 times 40 times 2 squared. Okay, so this is going to be, let's see, 20 times 4. Oh, so it's going to be exactly 80 kilograms meters squared. Alpha is going to equal sum of the torques over I. In this case, that's 5 over 80, which equals 0.0625. So it'll be radians per second squared. Interesting, okay. A little bit smaller. All right, so this is the second largest rotational acceleration. Cool. And then the hoop, what do you think? If all the mass is concentrated at the edges, this one should be very hard to move, right? Compared to the disc, probably compared to all of these. Maybe with the exception of this guy right here. We'll see. Are they similar? Which one is bigger? Right, make a prediction. Let's see. Rotational inertia for a hoop is just mr squared, right? So this would be 40 times 2 squared. We get 40 times 4. That's 160 kilograms times meters squared. Wait a second. That's exactly what we got up here. Interesting, interesting. Okay. And so that means the alpha is actually going to be the exact same thing, right? Because we have the same torque, same rotational inertia. That would be 0.03125. 0.03125 radians per second squared. So let's put all this together. That's interesting. They had the same exact rotational acceleration. So if we call this, how do we say this? We'll just call this alpha 1, alpha 2, alpha 3, 4, 5. Or maybe we give them actual names. We'll call this object, alpha of the object, alpha of the rod with the end, right, being the axis of rotation. Rod with the center axis of rotation. This would be alpha of the disc. And then this would be alpha of the hoop. So which one was the biggest? That was the rod. Let's see. That would be the rod with the axis at the center. That was the biggest alpha. Second biggest was, it looks like, the disc. Alpha of the disc. All right, third biggest was the hoop and the object, right? So alpha of the hoop was actually equal to alpha of the object. And then the hardest one to rotate was the rod with the axis of rotation at the end. So you actually could have predicted this entire lineup if you just knew which of these objects, or you just thought about which of them has more mass concentrated farther away on average from the center, from that axis of rotation. And if you think about it long enough, it should be obvious that this one is the one with the mass sort of pulled out away from the center farther, right? It's not going to be the hoop, actually, because think about it. All the masses here are only a distance 2m from the center, whereas in this rod, you have some little bits of mass out here that are more than 2 meters away from the axis of rotation. And that's a big deal because, remember, you're squaring the distance when you calculate this thing. So for a lot of these, you may not even have to do the calculations to make some of these comparative sort of guesses, right? So I thought this would be a really cool little way to see how to calculate moments of inertia, rotational, or in other words, rotational inertia for different kinds of objects. So I hope this was helpful. I hope, this is sort of clarifying some stuff. For my block 4A, guys, keep in mind you have a quiz later this week on unbalanced torque situations. So I'm just trying to give you more questions, more practice, and I'll go ahead and post this stuff in the drive if it's not there already, right? So we've done a lot with unbalanced torque, but one thing that's sorely missing from this practice is there's not a whole lot about angular momentum. So I think the next class, we're going to focus more on the relationship between torque and angular momentum, which is right here, right? This Mac Daddy equation right there. We haven't really pulled that out of our pocket for a lot of questions yet. So I'll try to add in more questions with this next class, and we'll get some good practice in. That should be Wednesday. So stay safe, enjoy the async day, and pray for the guys who are on Kairos. Have a good day.